Next, we define the concept of random variables. One of the motivations is the following. Consider again the coin tossing example. How could you possibly calculate the mean between heads and tails? We couldn't because they are not numbers. What about the following outcomes? Raining tomorrow or not raining tomorrow? How could you define the mean between those two? We can't. With that in mind, what is a random variable? A random variable is a function where each outcome omega in the sample space is assigned to a number which is denoted by x of omega. So here's an example. I'm gonna flip a coin. The possible outcomes are heads and tails. So the random variable x is the following. I am assigning to my first possible outcome a number 0, and I am assigning to my second possible outcome 1. So now I recoded my outcomes so that they are numerical. A function can be thought of as a recoding process. I am recoding non-numerical outcomes to a numerical variable. How do I assign probabilities? Well, the probabilities are the same as they used to be. The probability that the outcome is heads is half. Because I am assigning 0 to heads, the probability of x equals 0 is half, and so on. So basically, the probabilities continue to be the same. You have to link the outcome to the random variable, so you can link the probability to the random variable. The probability of a random variable is the probability of the outcome linked to that random variable. Now let's talk about notation. This is a function. This notation means function of, over here. In high school, you use f of x. Here is x of w, but the meaning is the same, function of. So x of w, the random variable, is a function of the outcomes. Sometimes it is denoted just by x or by some other capital letter. Now, many functions can be random variables. However, there are some restrictions. For instance, I can assign more than one outcome to the same random variable. It wouldn't be as useful in this case, but I could have assigned both outcomes to the number 0. I don't know what I'm going to do with this model, but I could have done that. What I cannot do, and that's because of the definition of functions, I cannot assign one outcome to more than one value of x. So, to assign heads to 0 and to 1 is not allowed. But to assign more than one outcome to the same number is allowed. Also notice that I could have recoded this random variable in many ways. Like I said, many functions satisfy the definition of a random variable. For instance, I could have recoded h to 100 and t to 1000. The problem is that model wouldn't be as useful. This is very useful. This is used for many binary real-life experiments, not only flipping a coin. But if I have recorded it as 10 and 1000, I'm not sure how could I possibly use this model. Now, we talked about the function that is linking the outcomes to numbers. Now, let's talk about the second function here that is linking the random variable to the probability. We are going to define the probability distribution of a discrete random variable. These notes and the next are all about discrete random variables. Soon enough, we'll be talking about continuous random variables. We'll talk about that later. So, a probability model of a discrete random variable x is the list of all possible values of the variable and their respective probabilities which sum up to 1. So basically, I simplified my probability model here by just listing the possible values of x already in their numerical form and their respective probabilities. If in an exercise you are asked to define a probability model, all you have to do is to set up this table here, a list of all possible values of x, which are already numerical because this is a random variable, and their respective probabilities. Now, some notation here. Know that capital X is the name of the variable and lowercase x is a particular value of this variable, such as 0 and 1. Now let's consider the example of rolling a die again. First of all, it's very easy to define this random variable because the outcomes themselves were already numerical. So it's much more intuitive than flipping a coin because the outcomes of flipping a coin are non-numerical, but in this case is. So when I define my random variable, although I could have chosen different numbers, that wouldn't make much sense, at least not to start with. So it's just the numbers 1, 2, 3, 4, 5, 6, and here are the probabilities. Back to notation, we're going to assume the following in this class. When we assign a probability directly to an event, which is a subset of omega, we use the notation similar to that of set theory. For instance, when denoting the probability of getting heads, we denote it by probability and then set theory notation here, h between brackets equals half. However, when we assign probabilities after we recoded the outcome to a random variable, we use the notation of functions, that is, f of 0 equals half. 0 is from this example here. Instead of h, I recoded it to 0. And the probability of 0, f of 0, is half. So, for our context, the following notations mean the same thing. That is, the probability that if we flip a coin, the outcome will be heads, assuming it was recoded to 0. Here, probability of heads equals the probability of x equals 0, equals f of x equals 0, equals f of 0 equals half. All these statements mean exactly the same thing. They are here to model the same real-life event. Again, this is usually used when we are talking about outcomes before we record the outcomes to a random variable. This one is usually used after we recoded the random variable, so f of 0 equals half, but they all represent the same event.